Because the main things were is like, their concept questions.
Oh, the streets are swollen.
Like, okay,
Then
I know this
doggies
concept, but I'm not.
rolling
Most of the times I felt
right.
like I might not especially
Good.
know, but I knew enough to make a good guess. So I just felt at least 50-50 on those. And there's
So, so guys, which came first, the chicken or the egg? That's a philosophy. When you're trying to teach some of these classes, that becomes a relevant conversation, because how do you understand this thing before you understand that thing? And where do you begin? And since I see Gavin sitting back there, will you be here Monday morning?
Yes.
We need to catch up on where Fox Maintenance is at, and I won't have time today, but can I ask you to come to me Monday morning?
Yes.
Thank you.
Thanks for reminding me.
So, you see all kinds of arrows and numbers handwritten here? Right up to the last minute, I'm trying, okay, what do I explain first? So, we're gonna start off with something that's a little bit in the weeds. Has anybody ever heard the term system effect?
Yes.
Yeah.
Oh, that's good. That makes me happy. There's an organization out there called AMCA. And it's the, I don't remember even what it stands for.
Air Movement Control Association.
Excellent. Excellent. These are the fan guys, and they are the ones that first built all the research facility and were heavily involved in establishing the standards for how you rate a fan and all that kind of stuff. The typical fan, we talked about a fan scroll, we talked about a fan wheel, right? The typical fan is rated with 10 duct diameters of straight distance, and then they put the little air probes down there after 10 diameters. And they construct the fan curve from this. So, the old school way, the way I learned, you start with the fan curve. But I'm talking about air handlers at the request of various people. And an awful lot of what you do with an air handler is dictated, at least to some degree, if you know what you're doing, by system effect. So if you're building your fan curve, all of your predictive stuff, on having 10 straight duct diameters coming off the fan, because you got to have some standard place to measure it, right? So that's what they do. How many real life projects do you ever design that have 10 straight duct diameters coming right off the discharge of the fan? It's pretty rare, isn't it? I mean, maybe you might have one up on a roof or something, but this doesn't happen very often. System effect is the correction factor, measured in static pressure, that you come up with to correct the fan curve, because the fan curve isn't right anymore if you're going to turn the duct over here. And the way that you fake that out or account for that is by adding static pressure, because when you're picking a fan, you pick it on how many CFM do I want to move against what static pressure resistance. So if you don't have 10 duct diameters and you really want to do it right, you add some additional static pressure to make up for the fact that you aren't doing it the way they did it in the lab. Okay? That's the concept of system effect. Now, I will tell you as a practical matter, if you're out here beyond, if you get 6, maybe even 5 straight duct diameters, most people don't bother with the correction because it's not huge. But there are several reasons why you might have to do it. Let's talk about velocity profiles for a second. You said, what's a velocity profile? Well, for one thing, the air going through this duct is not uniform through the whole duct. there's friction along the edges. This line duct, there's probably even a little more friction along the edges because, you know, that insulation is kind of rough. But you'll have a velocity profile out here somewhere, and one of the reasons they arbitrarily picked 10 duct diameters is because the theory was by the time you got there, it would be an even duct profile like that. Now the reason I drew it that way is because here in the middle is where the air is going the fastest, the biggest velocity, because there's less friction. Right along the edges, it's going at a lesser velocity. Now if you thought about that a little further, you'd realize that what that meant is you've got more air coming through the middle third than you do on the outside thirds, don't you? Because it's coming at a faster rate. But it gets as close to being smooth as it's going to be after 10 diameters. And that's the basis of the theory of why you pick 10 duct diameters. And I may have been a little extreme. It may not be quite so bad. Maybe it's like this after 10. But with this fan wheel spinning like this, when it first comes out of that fan scroll, it's like this, right on the discharge. Because, right, you can just see that centrifugal force. And so you've got a lot of velocity right there. And then as you go along, it gets better and better. Maybe it's more like this, and then it's more like this, and then eventually, you see the trend as you go further down the duct? What you can draw from this, and you know this from your own experience, you have seen fluids, whether it's in a creek or what you've seen how this works, because if you've got a fitting, let's call it an elbow. And remember, we're coming off with a velocity real high up here, down to almost nothing down here at the inside edge of the duct, okay? What happens if I put a rounded fitting here real close? Well, it certainly puts a resistance on it that you're going to have to correct on the fan curve. But you can continue this high velocity all the way around the outside, as opposed to doing what is colloquially referred to as breaking the back of the air. Let's say you did and let's make it even worse, let's make it a square elbow. Well, now what happens? You've got this huge velocity here, and we're going to try to turn it and make it go this way. What you get is a massive turbulent pressurization in that duct. You lose all the benefit of that velocity because it's virtually got to come to a halt, pressurize, and then move. That's a huge, huge difference. If you picked just the average forward curve fan and you picked it to move 5,000 CFM at 2.5 inches, this correction is going to be probably more than an inch. Now think about what that does to how much more horsepower you need, how much faster you got to spin it. It utterly invalidates the fan curve that was measured out here based on 10 duct diameters. You don't do this. This is a mistake. Never, never do this. Now maybe you've got a situation where you got a fan sitting here and the duct's got not much room and then it's got to go up. What do we do about that?
Turning bangs.
We can do things in the duct to make it better.
Change the fan.
Change the fan. What about that is the right answer, but what are we going to change on the fan? There's a word.
Direction.
Flip it.
Higher static pressure.
Well, we're going to change the configuration. Okay? What we're going to do is get the fan mounted like this. anytime you buy a loose fan, you will have a number of choices about how it's going to be configured. Always pick the one that works the best with wherever the duct's going from there. So, in this case, if we did this, now our velocity is really high here and very low there, and we can salvage, even if this is just a crappy, just a square transition, we can salvage some of that velocity. We can then further make it better. Sanderson put out lately, and I don't know who all he sent it to. Did any of you guys get the sheet metal fitting pressure loss sheet that he sent out 2 weeks ago, 3 weeks ago, something like that? I see some nods. Okay. What we had there were a choice of, I don't know, maybe there were 5 different ways of doing vanes. Or there were at least 5. And they also included the fact that this could be rounded. And the rounded isn't even just one version. There's short radius and long radius. And the longer radius you make it, the more gradual it is, and so the less losses you would have, right? As opposed to a short radius. I was always taught, and I think there was at least one surprise for me on Mike's sheet, but what I was always taught is that the least system effect elbow is a long radius, which makes sense, right? And it uses what our sheet metal guys here in Southern California call splitters. I had never heard that term before I moved to California. What we're really talking about are full radius turning vanes, which if we wanted to put in 2 splitters, you can see why they would call it that, right? You would have one that does this and one that does that. Now we've got 2 splitters, and we have taken the benefit of this, and we've got this velocity profile coming off of our fan that looks something like this, right? But we've sliced it into 3 segments. And so what we've done is we've limited the amount of turbulence, and turbulence ends up being one way to envision turbulence. This 10 diameters gives you as little impact on the velocity of the air as possible. But the more you start doing hinky things up here close to the discharge, the more you have changed the velocity and converted it to pressure. Because anytime this velocity of air hits a wall, some of it converts to pressure before it changes direction. That it comes at a cost. That comes at a loss of energy, okay? When you've got splitters, you have minimized that. Now, you get a diminishing return thing. Could we put 20 splitters in that elbow? Sure, but would we really gain anything? No. So, you know, if it was a really tiny duct, maybe 1 splitter is all you need. Maybe as it gets bigger, you'd want 2 or maybe 3. I've never seen really more than 3. Additionally, and I don't know how religious our sheet metal guys are at this. I can't say because I honestly don't know. If this is our elbow, these actually should extend slightly beyond the edge so that they slip into the next piece of ductwork. And that helps a smooth transition to that next piece of ductwork. Because what you're trying to avoid is turbulence. Any of you who've ever fished in a stream or a river, especially a stream with a sharp elbow, are familiar with the idea that if this is your stream and it's doing this and it makes this elbow, you're going to have eddies here, and that's where you want to put the hook, because that's where all the stuff is stirred up, and so that's where the fish are feeding, okay? The same thing is true here. You want to minimize, the turbulence happens for the same reasons, and you want to minimize that. I mentioned energy, right? That's one thing. I mentioned loss of pressure. There's one other different kind of, but just as important impact to turbulence. Anybody have an idea?
Sound.
Sound, yeah, that's exactly right. Duct rumble, which is what you call it in large ducts. And the broader the surface area of the duct, the more potential for rumble, bass drum type effect you get. That is all caused 100% by turbulence. We want to minimize that. So, long story short, you want to be able to come off of the discharge and go as far as you can before you change direction. You don't always have full control over that. You may not control the equipment room that it's going in, or there may be reasons you can't do what you'd like to do. But you've got all of these various fan configurations that you can pick from to try to minimize it. And like about the third thing that you do has to be this, if you're doing any kind of an equipment room that involves air movement. You got to sit there and think about, okay, do I want a fan that does this, or one that does this, or one that does this, or one that does this? And then there's the mirror image of all those. When you look in a catalog, or if you're looking at a catalog online, whatever, every loose fan that you pick will have, usually up very near the front of the catalog, one of the things you'll have to specify is which configuration. It's the same fan either way, right? But it's mounted in its little frame differently so that it will, work. If there is a motor and a belt drive thing, and some of them are ECM and direct drive now. Bigger it is, the more likely it is to have a belt drive. But where the motor gets mounted is usually on that back curve thing. So here it's there, but here it's here, and here it's here, and so the base, and you've got a fan shaft, right? So there'll be some kind of a support for each end of the shaft with the bearing and all that sort of thing, right? So where the motor goes varies with which one it is. So there's a couple of just standard pieces that the factory puts together to make these things go, right? You got a base that's like that, and a base that's like that for where the motor is, and yada, yada, yada. Additionally, if this has internal isolation, here's your base, there'll be springs under here. Well, the factory will only have certain springs they use based on the weight of all this. But the location of which spring goes in which corner is going to be different depending on where the motor is. It's also going to be different for the manufacturer. We don't usually get that sophisticated. But it's going to be also different for the manufacturer based on the rotation, because when that thing starts, it pushes down on this one and the one on the other side, right? And it also tends to stretch this one. You might even, in a really high static application with a lot of start torque, you might even have a snubber here that acts to hold the frame down with a little rubber donut in there. Okay, so you have to specify, and this should be on the equipment schedule, which configuration you're using. Another thing you've got to specify is which hand, right or left. There is no consistency in the world. And I'll give you one example, but the same is true for just loose fans like this. Air handling unit, which of course we talked about last week, is a cabinet fan. If it's a Carrier cabinet fan or a York cabinet fan, you're looking at the back end, the air's hitting you in the back, air's going this way, and that defines right or left hand. If it's Trane or McQuay, you would stand in front of it with the air blowing in your face, and that would define which is right or left. So one of the things you have to figure out if you're reviewing, whether you're designing it or reviewing a submittal, because you cannot end up with this thing in the field wrong, okay? So one of the things you have to figure out when you're designing it or submittal review, first thing is, okay, that manufacturer, and maybe it's Greenhecker, maybe it's Lauren Cook if it's loose fans, but that manufacturer, how do they determine right or left? Right or left based on what? Is it blowing in my face or is it blowing at my back? And then so you start there. Then you look at your equipment room. And if this is your equipment room and the air handler is over here in the corner and this is, here's your door and here's where you walk in, and so you want to use your pipe connections and you want to have the motor with the electrical connection and the motor access door. Okay, the air's coming this way and maybe it's going out the top. Okay. If this is a Carrier, that's a right-hand motor and a right-hand coil. Because for an air handling unit, you have to specify both, and they don't have to be the same. You might have a reason why you want the coil on one end and the motor on another end. But you have to specify both, okay? And so, if it's a Carrier, or my memory is a York, that would be right hand. If that's Trane, it's a left hand. Because now you're standing here blowing in your face, and okay? That is a point you don't ever want to foul up. So we've talked about that. Now, air handling units. So if I've got a horizontal draw-through fan, which means that it's horizontal, and I got a cooling coil, and I got some kind of little filter housing, and whatever else. This is a top horizontal front discharge. If, on the other hand, we were going to come out and go up, we'd want a bottom horizontal front. Or maybe we were going to do it this way. Well, that works really good unless you're going to have to turn and go that way, right? We already had that review. But let's say we're going to go up either straight or we're going to go up and come back. So this would be a, what do they call that? Something, discharge front, top, maybe top front discharge, I don't know. I haven't been a Carrier guy for 30 some years. And then let's say again that you were going to turn, you were going to go this way. Well, then you'd want a top rear discharge, or whatever they call it. I can't remember the initials now. This is another design thing, and it's another submittal check thing. Most consulting engineers not only don't know this, they don't specify it, and they don't show it. They just show the air handling unit, hopefully with the right dimensions, sitting in the room, and they leave it to the contractor and the equipment vendor to figure out which discharge do I get. And if you guys don't know what you're looking for, and you have the inside salesperson at Sigler or Trane or DMG or wherever you're buying your air handler, inside salespeople are the ones that start out not knowing anything, and that's how they learn. It's their educational process. I cannot count how many times when I was the Carrier manager, we would either catch it at the last second or then occasionally have to reverse one in the field if we ordered it wrong. Because if I give you a submittal and shows this, and I ship this, it's your problem if you approve the submittal. On the other hand, if I give you a submittal that shows this, and we ordered it wrong, and we ship this, that's on us, if I'm the rep. Okay? So, we've now talked about 3 things you got to review. You got to review the configuration on a loose fan. You got to review the hand of both the coil and the motor, and you have to, if it's an air handling unit, you have to review the discharge. Now, design got really lazy back. I moved here in '88. Back then, plenum fans were called plug fans. the plenum fan is the overall term. A plug fan is a smaller subset of plenum fans. And actually what we normally use are plenum fans, and the plug fan term is wrong. So at some point in the latter 90s or early aughts, people figured that out, and now they call them plenum fans. But we got lazy, and there's a whole lot of reasons we got lazy. I could go into it, but it's not worth it. And we started using plenum fans. Boy, that'd be a pretty bad angle for the belt on the pulley, wouldn't it? Maybe more like this. Okay, we started using plenum fans. And there's a trade-off with plenum fans. First of all, you don't have to worry about that 10 straight duct diameters, because you are not directly discharging the air out of the fan scroll and into the duct. Instead, all of the air you're using, unless you're coming off the plenum right like that, all of it, you lost all the velocity. All of it all goes to pressurizing the heck out of this plenum. One of the reasons that one of these is more expensive is because this piece has to be built hell for stout. You are pressurizing the heck out of that plenum. And that's part of the air handler. So it's got to be built really strong, okay? And so that's one of the reasons why this design is always more expensive. But it also takes more power. I mean, the waste inherent in doing this is significant. But you get two huge advantages. You get smaller footprint. And again, you don't have to worry about some hinky thing you did with the duct right off the discharge, because you could literally cut holes in this plenum any place you wanted to. Down, up, sideways, doesn't matter. You've pressurized the plenum. And again, with the exception of if you actually had a legit straight through pass from the fan, that would be a little better. But otherwise, it doesn't matter. You got a pressurized plenum you've tapped in. You spent a ton of fan horsepower to pressurize the plenum, but now you've got the benefit of it's just a straight duct calculation from there. You don't have to worry about system effect. You don't have to worry about any of that stuff. You paid for it right here. And the fan curve you get for this air handler, it's built around that. It's not built around 10 straight duct diameters. The manufacturer of this air handler will give you a curve that's built around the idea that you are pressurizing a plenum with it. And that's what the curve's based on. So you can be a really bad engineer, and if you do this, you're pretty much bulletproof. And that is my personal opinion of why in the 80s and 90s this became so popular, is because you didn't have to be as good, and you could be lazier, and etc. But then I'm a little cynical sometimes. Okay, so that's the plenum fan, and you'll see a lot of those. Now, three presidents of Western Allied ago, there was a guy named Pete Bordas, and Pete liked, at that time it was really common to be doing chilled water and an air handler per floor. That was a very common system in the 90s. What Pete would do, here's your metal deck of the room, you know, and then they pour the concrete, and then you go up to the next floor. And here's another floor. And you generally, outside of the equipment room, there was a hallway. And the metal deck, you know, continues through the whole floor. And then the duct would pass over here. Does anybody know why? This is called tunneling. That's as opposed to having the walls go all the way to structure. Does anybody know why, the number one reason why we want to tunnel instead of go all the way to structure? What do you got to do if this hallway is a fire exit, emergency exit? What do you got to do if it goes all the way to structure and your hallway's in here and a duct goes through it?
Right.
That helps. Combination fire and smoke dampers. Now, there are certain instances where you can get away without using them if you use a certain gauge of metal and it's less than this size, and that's a Brian Sabisma thing. He loves these more intricate code questions. But for the most part, you end up doing this. When we built the mechanical system for Kerlan Jobe in 1997, and Kerlan Jobe Medical Center, which just changed its name because Cedars bought them. But Frank Jobe invented Tommy John surgery. I think I mentioned this in one of the previous classes. The architect was an idiot. He was bound and determined that all the walls were going to go to structure. So here we have a suite. It's got 4 operating rooms and a sterilization room, which has to be at negative pressure, right? You got to keep the ORs at positive pressure. And various and sundry other things. In this, and the sterile corridor that goes by outside the ORs and the sterilization room and the storage room where they keep all the surgery supplies. And there's a bunch of specific things that you have in every one of these surgery centers. We've got one air handling unit, and my memory is, well, Matt Calabrese did a renovation recently, and he put either a 40 or a 50-ton rooftop air-cooled chiller up there to support this air handler. It had been on the house system. So 40 or 50 tons of air. Anybody want to guess how many combination fire and smoke dampers there are in that one suite that is completely floor to ceiling walls? Take a guess. How many combination fire and smoke dampers? Well, let me back up. Well, no. Take a guess. How many combination fire and smoke dampers? Just take a wild ass guess.
10.
8. There's like 120. Had we tunneled it, which Pete suggested early in the process, would have been really easy to have tunneled it so that, you know, these ducts are going over the top of the thing and you don't have to worry about those combination fires. Had we done that, we'd have had about 18. So the difference was about 100 combination fire and smoke dampers. Now you got to buy the fire and smoke damper. You've got to frame it in. It's got to connect to the ductwork. You have to get power to it. And you have to tie it into your fire and life safety system. Another thing in your design considerations that you always want to be looking at is, how do I minimize those? I mean, they're important and we need to have them when we need to have them, but we can be stupid and magnify the number of them by just unbelievable amounts if we don't think. Or if we think but then don't communicate. So, what Pete used to do, getting back to that, he would get I drew a horizontal draw through already, right? So a vertical draw through looks like this. Here's a cooling coil, drain pan, condensate drain, fan, I'll draw top horizontal front. We got the filters, and then maybe we got some mixing box dampers or whatever. What Pete would do, this would have been blowing probably right about here. So Pete would put a stand in the room, and then he would put the vertical draw through air handler on here so that the fan was arranged like this. And then he'd run the duct across overhead. And he, honest to God, sometimes he would actually get 10 duct diameters. And then what you did as sound insurance is you would have 2 layers of 5/8 inch chipboard crossways. Because when you do that, that is a pretty effective duct rumble inhibitor. And so you would have a pretty straight shot there, so you'd minimize the duct rumble as much as you could. And then on top of that, you've built the tunnel so that it helps you too. And if you were really sensitive to it, you'd put some sound absorbent stuff across the top here. You also obviously did not use lined. You used, well, excuse me, you didn't use wrapped, you'd use lined for typically till you got the other side of the corridor. I mean, that could be 10 feet, it could be 15. He did a couple of different things. I don't know where he was on that subject at the end of his career, whether he was doing 10 or how many feet he was, I don't know. But you'd have line duct, you'd have, if you were concerned about it, some additional stuff, you'd have the double wall jip, and you would have put it on a stand, and the height of this stand, that was the last thing that was determined based on the equipment submittal for the air handling unit and where you could get this thing to be right where you wanted it to be going over the tunnel. Does that make sense? So that's some of the games you play when you lay the thing out if you really want the results to be good. Okay, so we went backwards. We've used half of our time. Now I can go to item 2. We talked about left and right hand. We've talked about discharge configuration. We talked about how you fit it in the equipment room. You know what we haven't talked about with air handling units is blow through and dual duct, whether it's dual duct with mixing boxes or dual duct VAV. So the standard dual duct air handling unit would look like this. And it would discharge with a little flex. It would discharge into the plenum. There'd be a cooling coil sitting here. And then there'd be a heating coil up here. Yeah, you know what? Let me try it this way. Yeah. Be a heating coil here. And why is the heating coil smaller? There's 2 reasons.
Technically, to reheat coil.
No, it isn't. Because this is cooling, right? And this is heating, so this is not reheating air you cool. So no, this is not reheat. That's an important point to
Well,
bring
where's
up.
your outlet? I thought it was going up, sorry.
Well, we'll draw that, but I'm starting. First step is, why is that heating coil so much smaller than the cooling coil? There's 2 reasons.
Less delta T.
Less delta T is the reason, but then that leads to some things. Typically, in more or less, you're cooling air 20 to 25 degrees, but you're probably heating air 40 to 50 degrees. It's roughly double. So if let's say the heating load was equal to the cooling load. Let's say they were the same load. You'd need half the air here because you're heating it twice as much. Does that make sense? With twice the temperature difference, we need half the air if their loads were the same. Now in Southern California, usually the load isn't the same. Usually the heating load is actually a little lighter. So that would make it even more so. But there's one more reason. I can't hear. I'm old. What's the other reason the heating coil can be so much smaller?
You don't really need heating here as much.
It's the face velocity. You say, well, what's that have to do with anything? Well, that coil's wet. Rule of thumb is you never, ever want to exceed 600 feet per minute on a cooling coil, and that's sketchy. You can do that on a VAV unit based on the idea that it'll very seldom ever be at maximum airflow, okay? Most people will tell you that the max is probably 550 to 575 feet per minute. The recommended maximum on a heating coil, depending on the manufacturer, is usually about 750. Because there's no water to blow off. And this is probably a 6, maybe an 8-row coil. And this is a 2-row coil usually. So the pressure drop is a lot less. So you can get away with a much smaller coil, and I've drawn it that way, and that's not grossly out of scale. That's more or less what it's going to look like to you in the field. And so you're going to have a big cooling coil and a much smaller heating coil, and then you're going to have the opening up here, and you will turn out, you will do the long radius turning vane thing to get up into the ceiling, and this one will be going straight up into the ceiling. And then you're going to run a heating and a cooling duct throughout the floor. Which one's on top? Heating. Why?
Smaller.
Because it's littler. That's the whole reason. So then so if you look at a floor plate here, and we've got an equipment room sitting here, usually next to the elevator somehow, and we've got some kind of, and I'll draw it this way, this is not the most efficient way to do it, but we've got some kind of a loop going around. You might do an H, there's more than one way to do it. But when you look at this duct traveling around, what you've got is a bigger cold duct with a smaller hot duct on top. So that you can see the difference, I'm going to draw both, okay? Now, if we've got one zone that we want to cool or heat, back before 1973, the way that we would do this is we would use a mixing box usually. So you got a cold duct, and you got a hot duct, and you would come off here, and you would come off here, and you'd go to a mixing box that would have one damper and one actuator. And you'd have it coming out, and it would end up in a ceiling diffuser blowing into space, and there'd be a temperature sensor of some sort on the wall. And this would go back up to a single actuator, which would just do this. Now, there's a lot of problems with this, but it's cheap, and it does a great job of temperature control. Plus, you never get a draft, because you're always at full airflow, right? So this was what, if this was before 1973, anywhere in the United States, and you had a dual duct system, and they were relatively common, you would have typically dual duct mixing boxes, and that's what that would be. But then the Arab oil embargo happened, and either 75 or 76, ASHRAE, it took a couple of years to put it together, came out with Standard 90. And then California picked up Standard 90 and made it part of Title 24 a couple of years later. I don't know, I want to say 79, but that's close. They didn't radically change this, but what they did is, first of all, they put a line here and a plenum. They got an independent damper and another independent damper. They've got two actuators, typically one controller, but two actuators. And you could do anything you wanted with those two. Title 24 from way back didn't want you mixing mechanically cooled and mechanically heated air. But you could work with the cooling air, take it down to a minimum. You could work with the heating air, take it down to a minimum. You could shut either one off. There was generally a ventilation air code requirement. So you'd have to have some air going in. So what do you do if the room is happy the way it is and it doesn't need any air at all? Well, what you're going to end up doing is giving it usually a little bit of cooling air. Although, I mentioned earlier CO2 sensors. If you're not measuring any CO2 in the room, you can shut them both off. And there are some other things you can do. Consult with Brian. But dual duct VAV is a very common system. Now, the temperature of the air in both of those ducts can be reset. And so we are typically going to operate a cold duct between 50 and 55. But the hot duct could be anywhere from, oh shit, maybe 85 up to 130. You say, why would we need 130 air in LA? Well, the answer is that depends on how you define need. In Buffalo, you probably need 130 degree air on the coldest day. Here, you would never need it, but what it would let you do is heat up the building really fast Monday morning after it's off for a weekend. Dual duct doesn't really need a morning warm-up cycle with separate equipment and separate stuff, because a dual duct system is set up to give you whatever you need when you need it, and for that reason, it is one of the systems that the CEC, California Energy Commission, thought would probably come out of this heat pump boiler thing. Because with 135 degree water, you can make 110, 120 degree air, whatever you need, 100 degree air, real easy. And so the CEC thought we were going to see 4-pipe fan coils and dual duct VAV. That was the two, initially the two, I want to say those were prescriptive solutions that you didn't have to do anything for. Now they're not the lowest cost systems. And you could even argue, that they're not even the most efficient, maybe, depending on your situation. So what's the other one? Performance, right? As opposed to prescriptive. The performance requirements have gotten a lot of attention since the CEC first came out with these ideas. And what you found is people are still using VAV reheat predominantly today. But it will be interesting to see the track record of the heat pump boilers over the next couple of years. If they fall on their face and the public at large determines that they're a piece of shit, then I think you're going to see more fan coils and more dual duct, because they are more forgiving of having cooler heating water temperatures. On the other hand, if they're a wild success and there's no issues and nobody has any problems, I don't think we're going to be changing away from single duct VAV reheat anytime soon. Okay, so we talked about dual duct, we talked about mixing boxes, and we talked about dual duct VAV. Now let's spend some time on single duct VAV, because that's mostly what we do in commercial office buildings, or commercial buildings of all sorts. So I got a cooling coil, and I probably have a preheat coil, and I got a filter bank. If I don't have a preheat coil, and I don't have a DOAS, has everybody ever heard of a DOAS? What does that stand for?
Dedicated outside air
System. Yes. This is a little air handler on the roof. Well, it wouldn't have to be little. If it's a big building, it might be a big air handler on the roof. But it's an air handler on the roof that handles 100% outside air. And its role in life is to take the outside air and distribute it down to every air handler, every fan coil, whatever's down there that's taking ventilation air, and it will filter it, and it will generally cool it down to a room neutral temperature, 72, something like that. And it will generally heat it, if it's cold outside, it will heat it up to 70 or so, okay? That serves the purpose of your morning warm-up on those cold Monday mornings. It also serves the purpose of the morning cool down on Monday morning when your building got to be 130 degrees over the weekend when you had the AC turned off, right? So the DOAS shoulders that burden. But if you don't have a DOAS, then you've probably got a preheat coil here, and you've probably got a cooling coil. This goes out to a duct, and there's branches, and then you've got a takeoff to a VAV box, which let's just say it has a heating coil, and comes off and ends up going down to some diffusers. There's a stat on the wall or a temperature sensor or something. That looks familiar, right? This is what we do all the time. How does that fan know what to do? I mean, the control system will enable it, but it enables the whole system. But how does it know variable volume, right? Various boxes are doing more or less or some, or how does it know what speed to run at? Well, let me tell you what it doesn't do. We don't count the CFM at every VAV box, total it up, compare it to what we're measuring there, and speed the fan up or slow the fan down to make the total here match the total there. We could do that. We could do that. Virtually every VAV box today has got a airflow sensor that's kind of sort of accurate. And it's not unusual for the air handler to have one too. So if we wanted to go to the effort of doing that, we could. And that would be a direct way to control that fan. But we don't do that. Cost is one reason. It's also kind of clunky. What we do instead is we use an indirect method. What indirect method do we use to tell that fan how fast to go? Somebody say duct pressure, thank you. There you go. The conventional idea, you know, wives' tale conventional item, is you go 2/3 of the way down the duct and you put a little pressure sensor here. And that pressure sensor is set for some number. And that signal goes back to the controller that tells the variable speed drive what to do. Variable speed drives are pretty remarkable little devices. You can get a variable speed drive with one of those controllers built right in, and you wouldn't even need an external automation system of any sort. You could just have a VSD with a controller and a compatible pressure sensor, and they're their own standalone little thing. That was what we did back in the day when everything was pneumatic and you know, time clocks were used to turn things off and on, and then we would typically just do that. Today, I think we much more typically integrate all of this into the automation system. Okay, how do we know how many inches? You start back here. You look at the design CFM, and let's say that diffuser was going to put out 600 CFM. You pick the diffuser, and you see, okay, what's the static pressure drop through that diffuser? Let's say that, I don't know, I'm making up numbers. Let's say that the diffuser pressure drop was 1/10 of an inch. Then you look at the flex duct that you've got going back to the VAV box. Is it a short run? Is it a long run? Does anybody really care? Do you just throw an arbitrary number at it? Now we're getting closer to reality. But let's say you did another 1/10 of an inch for the flex. Then you got the VAV box with a reheat coil. Because with the reheat coil, there's more resistance than without, right? So what's a good number for a VAV box with a reheat coil? Anybody got a number they like?
0.5.
That's 0.5 is probably a little heavy. It's all of 0.3, somewhere in between. I don't know. Let's put 0.4 just for the sake of argument. Now you've got the high side duct, and when you're talking to the sheet metal foreman, and it's a TI job, and you're putting in VAV boxes, he's going to talk to you about high side and low side. Well, the low side, why do they call it low side? Because it's lower pressure. So you've got a damper in there, right? You're having to give this box a certain amount of pressure to get the air out. How much pressure do you have to have right at this point? You have to have this much. I mean, if these three numbers are accurate, it'd be 6/10 of an inch. We often get by with 5/10, but okay. So we got 6/10 of an inch at that point. Well, then you've got, and how far this thing has got to run is a factor. If it's got to go a long ways, they're going to use spiral and they're going to wrap it. If it's a short little amount, they might not even use metal duct. But you've got that high side, whatever that is. I'm just going to arbitrarily say that that's 1/10 of an inch. Except we've got to come off of the duct, and there's a loss at that fitting where the duct comes off the main, you have a loss just making the corner because it doesn't smoothly make the corner. It's got an opening and it leaks out. And it leaks out as a result of having pressure in the duct pushing it. You would think pushing it perpendicular, but if we use the right fitting, it's not exactly perpendicular. You get a little bit of velocity help. Okay, so maybe it looks like this. But that plus the high side is probably not going to be 1/10. I'm going to call it 2/10 just for the sake of argument. And then that means that I have to have 8/10 of an inch right there. And I'll tell you that's low. I probably underestimated in here somewhere because almost always you need at least 1 inch to 1.25 inches. Now if you see, so where are we going to put this? If we put it right here, right there, then based on what I got here, it's 8/10 of an inch. Like I said, that's low. It should be a little higher than that. But if this is out near the end of the run, this one that we got here, and we've just put this 2/3 of the way, well now we've got to also measure the pressure differential between there and here and add that, right? So maybe that's 2/10. And so maybe this is 1.0 inches, which is still low. If you hear somebody running at 1 inch, I always wonder if the very last guy, last little piggy at the end of the litter is actually getting anything. May not be, okay? Because that's still on the low side. But today, because we have super duper bitchin' digital controls, we can do a global analysis of all the room set points and see how far off we are. Let's say the room was set for 73. Let's say all of them are set for 73. You know they won't all be the same. But you look at the differential. And if the warmest room is 73.5, so you're within 1/2 degree, well, maybe you can ratchet down that pressure because you are meeting the load, right? This is an adjustable set point on the automation system. And let's say, on the other hand, we do a global thing, and all of the offices facing, with the glass facing the sun, they're all a couple degrees warmer than they should be, and the box is wide open. Okay, we aren't putting enough air into the duct now, are we? So now that same analysis can cause us to bump up the pressure that we're maintaining in the duct. It's kind of a dynamic thing. Back in the day, we just set it one pressure, and of course you set the pressure for the worst case, and so you wasted a fair amount of energy just pressurizing that duct, more than you ever needed to. Today, if we do it right, and some of this is mandatory with Title 24, and some of it is a couple of different paths you could follow. You could do it this way, or you could do it that way, and either one would be acceptable, okay? But that's how we control those things today. Oh, we've got time for one more topic. What if you've got a big bus depot or railroad depot or county fair building or some other big barn? How many zones is that? If you want to be cheap, it's just one zone, isn't it? So you get rid of all this shit. All of it goes away. And the duct comes out, and you're probably measuring the airflow, but the duct comes out and it branches in a couple of places, you know, with some diffusers for the barn. And maybe you don't even have that kind of diffuser. If it's a big barn, it's probably some kind of a horizontal blow thing, you know, whether it's those Seho eyes that you see that turn around with the round outlet, or whether it's just horizontal, you know, grills set up. You've got one sensor out here, and you got to think about where you want that to be. if you really insulate the barn wall on the sunny side, and I mean really insulate it, you might get away with a single zone. And if you do that, what's controlling the speed of the fan now? It's not some duct pressurization thing, is it? We're not pressurizing a duct. What's controlling the speed of the fan? The room sensor. Right? If it needs more air, it speeds the fan up, and if it's plenty cool, it slows the fan down. That's called single zone VAV. Works great. Churches do that. I mean, any kind of big honkin' assembly hall sort of a thing. And let's say you weren't sure, because, and church is a good example. You've got that front area with all the lights on the guy with the golden hair that's asking for your money, right? You've got that at the front, and most of the rest is different. So do you put in ductwork and VAV boxes, or do you just get a second single zone air handler for just the stage? And that's what people really do. And so, and it's not just churches. I mean, any kind of a theater where your live performances up on a stage with all those lights. And the light load with LEDs is not near what it used to be. It's a ton less, in fact. And it's not just stages where that's true. It's also operating rooms. You may never have thought about this, but the typical OR with the honk and halogen lights just over the shoulder of the surgeon, they didn't just dump heat into the room. They were putting radiant heat on the back of the surgeon and whatever nurses were at the front, the anesthesiologists probably too. Okay, all of those people were getting radiant heat, and that's why they wanted to keep the room as cold as they could get away with. You'll never find a surgeon who doesn't want the room down to about 63 degrees. Did I tell you why you don't go below 60? That's the anesthesiologist. If you're in a room below 60 and he puts you into general anesthesia, you might not wake up. So there's a hard cutoff, and everybody has their own. I think Cedars number is 60. Colonel Jobs was 60. But there's a hard cutoff on how cold an OR can be, only because of what the anesthesiologist is trying to accomplish, okay? But some safety factor above that, 62, 63, 64, that's what all the surgeons want. And the older ones, and older means past 35, because LED surgery suite conversions have only been a thing for the last dozen years. You get a surgeon who is used to the halogen lights over, and he wants it cold, even when he doesn't have the radiant heat all over him. Now, if you know very many OR nurses, the second layer of people around the table are wearing mucklucks because it is so cold in there. And so it was definitely a stratified society in an operating room, especially in the old style lights. With the LED lights, the heating load in an OR is like less than half of what it used to be. The driver now is probably the ventilation air in terms of load. Okay, so that's the little speech. Single zone VAV. And if you go single zone VAV for a barn, but you got one particular area you're concerned about or two, go with a little bitty single zone VAV. Or if it's small enough, just a little constant volume fan coil. But if you can do the bulk of the room with single zone VAV, it's also very efficient, but it's definitely the least expensive way to go. Okay, we didn't talk about chilled water reset much. Our ability to do chilled water and hot water reset, in other words, adjust the temperature that the chiller is making or adjust the temperature that the boiler is maintaining in the loop, our ability to do that is dramatically improved with digital controls. Because now, instead of looking at 1 point or 2 points and making a decision, if we choose to, we probably have all that information available globally. It's just a function of how many sensors we got, right? You've got all those room sensors, and you probably have some sensors in the piping and so forth. And so you can use that data, and you know that your slam dunk meeting the cooling load, no problem. Well, now you can start to jack up the water temperature. But I think I told you, and a lot of people do that, but I think I told you that you probably use more power on the fans than you do on the refrigeration plant. It's usually like 60-40. And so where you're really better off is keeping the leaving air as cold as you can get away with without having draft complaints. And that's counterintuitive, because when you talk to building engineers, they're going to think, well, making colder air costs me more money. Well, it does cost them more refrigeration. But this is variable volume. If we're making the air colder, we're giving them less air. And you save more on the air, like 1.5 to 1. You save more on the air than you spend on the cooling. And so that is a wives' tale you're going to run into forever. You're going to run into building engineers for the rest of your career who are running the chillers too cold, or excuse me, too warm, because that's their single biggest items. That's the truth. And they're saving energy there, and that's the truth. But they're giving it away plus some on the fan side. So when you're doing reset of either air or water, again, if energy is your concern, you want the air as cold as you can get away with without draft complaints. And then once you accomplish that, then you mess with your chilled water temperature as long as you can maintain what you were trying to achieve on the air side. That's all I got today. The next topic, we're going to start talking about duct classification and also various kinds of fan-powered boxes and when you would want to use those. Because we're just talked so far about the straight VAB box. But there's two flavors of fan-powered box that have a fan built into them. Obviously, that's going to be a more expensive box, and we have to run electrical power for the fan. So there's a cost component, but there are also places where they're very handy, where they fit. And in Southern California, we don't generally use them as often as we probably should. So that'll be where we start tomorrow or next week. Thanks, guys.